Let's talk about type 1 and type 2 errors. The drug Avandia is used to treat type 2 diabetes, but a 2007 article in the New England Journal of Medicine indicated that the drug might increase the risk of a heart attack. Of all people with type 2 diabetes, one would expect 0.360% of them to suffer a heart attack during a 7-week span. Suppose that in an overall sample of 5,000 type 2 diabetes patients taking Avandia, 25 people had a heart attack during that 7-week span. Find the null and alternative hypotheses. The null hypothesis, as always, means no change, no difference. Take Avandia, don't take Avandia, not going to make any difference with regards to heart attacks. The alternative hypothesis is that there is a difference. So in this case, the null is that the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span is 0.00360. If we want to represent this symbolically, we would just say let P equal the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span. And then our null hypothesis is that P equals 0.00360. Our alternative hypothesis is that P is greater than 0.0036. We choose this as the alternative hypothesis because we want to test the hypothesis that the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span is greater than 0.0036. That's what we were told earlier. That's what we want to test. Okay, there's how we define P. There are null and alternative hypotheses. Let's calculate the test statistic Z. And again, this is the formula for Z because we're dealing with proportions. Here, P hat is the proportion of success in the trials. That's 25 divided by 5,000, although I'm not sure that having a heart attack is really much of a success. P0 is the conjectured value of P in the null hypothesis. That was 0.0036. Okay, our test statistic, when you plug in everything, including n equals 5,000, is 1.653. So draw your conclusion. Well, in this case, our alternative hypothesis is of this form. P is greater than P sub 0. The rejection region will be of the form Z is greater than Z star. Oh, but what is Z star? Well, since we're dealing with a one-sided hypothesis test, this is the chart we want to use for 95% confidence intervals or 95% confidence levels. Z star is going to be 1.645. Since our alternative hypothesis is one-sided and of the form P is greater than P0, we reject that null hypothesis if the Z score is too far to the right. Again, if Z is greater than 1.645, that corresponds to a P value, or that corresponds to a value of P that's too big, a proportion that's too big. Okay, our Z score is 1.653, which is greater than 1.645, so we conclude that the null hypothesis is false. We reject that null hypothesis. Find the p-value. What's the p-value? Well, if the null hypothesis were true, the probability that we would get a z-score of 1.653 or even more extreme is, let's look at the chart. Our alternative hypothesis is of this form, so the p-value is the area to the right of z. The p-value is the area to the right of z, so we use this command on the TI. In other words, we enter normal CDF, 1.653, 10. That will tell us the area to the right of z. Z is 1.653. And again, 10 is so far to the right, it may as well be positive infinity. We get 0.0492. That is our p-value. So p is 0.0492. If the p-value is less than 0.05, we reject the null hypothesis in general. If the p is low, the null must go. So there's how we define p. There's our null and alternative hypotheses. We reject that null hypothesis. So here's the way we state our hypothesis test conclusion. Again, if it's mere 0.05, our chosen level of alpha, we say there's some evidence to conclude that the alternative hypothesis is true. But we state in terms of the original problem. Okay, there's the way we define P. There are our null and alternative hypotheses. We reject the null hypothesis. There is some evidence to conclude that the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span is greater than 0.0036. And again, when the p-value is close to 0.05 or our chosen value of alpha, we simply say there is some evidence to conclude that, rather than saying, oh yeah, absolutely, there's no way the null hypothesis is true. We don't say that because in a sense, 0.05 is kind of arbitrary anyway. Our p-value 0.0492 is close to 0.05. Why not choose 0.01 as the cutoff? Well, we could do that, but in trying to avoid one error, we might cause another error. We traditionally choose 95% as our confidence level. If the null hypothesis is true, there is a 95% chance that we will accept it, and consequently a 5% chance that we will reject it. In other words, there's a 5% chance that we'll obtain data that will force us to reject it. That kind of error would be called a type 1 error. It's rejecting H0 when H0 is true. You don't want to reject H0 if it's true. The probability of making a type 1 error is alpha. We use the Greek letter alpha to represent it. That's our level of significance. Again, that's the probability of rejecting H0 when H0 is true. Now, a type 1 error is the probability of rejecting H0 when H0 is true. That's the probability of a type 1 error. It's alpha. It's the level of significance. The Greek letter alpha is used to represent that. That, again, is the probability of rejecting H0 when H0 is true. In the context of the problem, you're rejecting H0. You're concluding that P is greater than 0.0036 when H0 is true, when P really is 0.0036. In other words, you're concluding that Avandia is increasing the risk of a heart attack, but it's not. The reason you don't want to make an error like that is because the FDA might yank Avandia from the market, even though it's not causing any problems at all. Here's what this represents graphically. Okay, so if the probability of causing a heart attack is 0.0036, most of the time, you're not going to get some weird data that's going to force you to reject the null hypothesis. But every now and then, even if P is 0.0036, you might get a p-hat that's really large. You might have a big batch of heart attack victims in your sample. And that might lead you to reject the null hypothesis. That would be a type 1 error. We don't want to do that. Type 2 error, that's failing to reject H0 and H0 is false. Probability of a type 2 error is beta. In other words, that's the probability of failing to reject H0 and H0 is false. In the context of the problem, you're failing to reject H0. You're concluding, oh yeah, P is about 0.0036 when H0 is false, when P is really greater than 0.0036. In the context of the problem, you're concluding that Avandia is not risking the risk of a heart attack, is not increasing the risk of a heart attack, when it really is. You don't want to do that. So yeah, that'd be bad, because you might have people taking Avandia when they really shouldn't be. Maybe that drug shouldn't be on the market. The power of a test is 1 minus that. So again, beta, that's the probability of failing to reject H0 when it's false. 1 minus that, that's the probability of rejecting H0 when H0 is false. That's what we want to do. We want to reject H0 and H0 is false. We call that the power of the test. So again, it's the probability that we reject null hypothesis when that null hypothesis is false. It's like the power to sniff out a false null hypothesis. In the context of the problem, that would be the probability of concluding that P is greater than 0.0036, given that P really is greater than 0.0036. If we had chosen 0.01 instead of 0.05 as our level of significance alpha, would we still have rejected H0? No. If the p-value is less than the level of significance alpha, usually 0.05, we reject the null hypothesis. Suppose we chose 0.01 as our level of significance. In this case, our p-value is 0.0492, which is greater than 0.01, so we'd fail to reject H0. Again, if you make the p-value small, if you make your alpha smaller, it just makes it less likely that you're going to reject that null hypothesis. By the way, the FDA has concluded that the diabetes drug Avandia does not increase the risk of a heart attack, but not everyone in the medical profession is convinced of that.